So chapter 4, if we go by number of topics, actually isn't all that long. So like the title suggests, we will be discussing electromagnetism. So here are some of the kind of questions that we might discuss. The first topic will be mostly talking about this first question: how are magnetic forces used to produce rotation in an electric motor? So why does an electric motor turn when you supply an electric current? What is a brushless motor? Okay, so there are different types of electric motors. There are brushless motor and there's brushed motor. How can the concept of electromagnetic induction be applied to benefit human beings? That is topic 4.2, electromagnetic inductions. And the last one, why are transformers used in the transmission and distribution of electricity? So that would be chapter 4.3. So yeah, 3 topics, not too long. And I don't think not as many formulas as the last chapter, which had a lot, but still very interesting and very practical and very likely to come out as a KBAT question during the SPM. So force on a current carrying conductor in a magnetic field, electromagnetic induction, and transformers. All right, so let's go straight to this first topic, and let's just try to understand what this topic is about. What is this? So, force on a current carrying conductor in a magnetic field. We know what force is, right? We know what force is, and force causes movement, it causes work, it causes all kinds of things to happen, right? We know what a magnetic field is. We've studied magnetism way back in Form 2. And so we understand that there is north and there is south, and the magnetic field moves from north to south, and that magnetic fields have a pushing and pulling force. You know, so if it's the same poles, north and north, they push each other, and if it's different poles, south and north, they will attract each other. So we know those 2 things. Now, what is a current carrying conductor? Right? We know what a conductor is. Something that will allow electricity to flow with it. So a current carrying conductor is any conductor that has a electric current flowing to it. Basically, if I really wanted to make this simple, it's basically talking about a wire, right? But of course, in physics and in science, we have to be very specific. You know, it might not always be a wire. So we use the phrase current carrying conductor. But if we were to simplify this title, we would say force on a wire in a magnetic field. That's basically what we're saying. Okay, but it could be any kind of conductor, any metal that is currently carrying electricity. So just from the title alone, we know that any wire or any conductor in a magnetic field that has electricity, there's going to be some force happening. So that's the basic idea, but the details are what we need to find out. All right. Force on so do you know that an electric train, as shown in photograph 4.1. Did I put the photograph? No, I didn't. Okay, so I forgot to put the photograph from the textbook, but there is the photo in your textbook. That would be in page, let me check. Page 136. So on page 136, there is a picture of an electric train. So an electric train, as shown in photograph 4.1, uses a large electric motor, while a smartphone, so these, uses a small motor. The function of most electric motors is based on the effect of once again, a current carrying conductor in a magnetic field. So once again, you see that term. So it's quite important. When a current carrying conductor is placed in a magnetic field, the conductor will experience a force. The direction of the force depends on the direction of the current and the direction of the magnetic field. So these 2 things we have to think about. what is the direction of the current? Which way is it flowing? So where is the positive side and where is the negative side? And where is the direction of the magnetic field? Meaning to say, where is north and where is south? So depending on the interaction between these two things, okay, where is the plus and minus and where is the north and south, you can change the direction of the force or control where that force is going. So again, I forgot to put in the picture. Figure 4.2 shows a current carrying conductor that is placed in a magnetic field produced by a pair of Magneder magnets. So what is the direction of the force acting on the conductor? So like I forgot to put in that picture, but maybe I can just show you. I think those. So basically what we have here, yeah, okay, never mind. That's not working at all. Okay, but just basically it's a picture of a wire between two magnets. That's literally what the picture is. A wire that's carrying current or carrying electricity, and it's between two magnets. And that kind of thing is actually going to produce a force. So why does it produce a force and how? That is the question. So the force on a current carrying conductor in a magnetic field is produced by the interaction between two magnetic fields. So actually, there are actually two magnetic fields going on. The first magnetic field is the permanent magnet. So when we have a wire going through some permanent magnet, the permanent magnet, of course, it already has its own magnetic field. However, we also studied way back in Form 1 that any wire that has an electric current also produces its own magnetic field. So when we have two magnets next to each other, I think maybe you can start to imagine what's actually happening here. There are two magnets, two magnetic fields. One is the permanent magnet, one is the electromagnet. And remember that both the permanent magnet and the electromagnet have a have a north and south pole, have its own magnetic field. So because of this, we remember back in Form 2, the different poles, they push and pull each other. And so it is this interaction between these two magnetic fields that causes the force. It's the natural force between the north and south pole of a magnet. And so that's very interesting. So the genius or the great thing about this is this gives us a certain amount of control. The permanent magnet, you can't really control it because it's a permanent magnet. But the magnetic field from the electric current or from the electric flowing through the conductor, you can control that somewhat. You can control it by changing the amount of electricity or amount of current, I should say. You can control it by changing the shape of the wire. All kinds of things that you can do to control. And this thing that allows us to use electromagnetism in so many different ways, including most commonly by creating electric motors. So the two magnetic fields combine to produce a resultant magnetic force. So resultant meaning to say, when we combine the different forces, what is the resultant force? Right? And so you have a resultant magnetic force that is also known as a catapult field. And the pattern of the catapult field will show the direction of the force acting on the conductor. So by taking a look at the magnetic field and by taking a look at how the field interacts with each other and the resultant magnetic field, we can predict and control the direction of the force acting on the conductor. So I did put in that picture. Yes, I did. Okay, so figure 4.3 shows the catapult field formed when a current carrying conductor is in a magnetic field. A catapult field is a resultant magnetic force produced by the interaction between the magnetic force from a current carrying conductor and the magnetic field from a permanent magnet. The catapult field exerts a resultant force on the conductor. So let's take a look at it. Okay, so here is what's happening. So let's take a look at it. Let me zoom into this picture just a bit. And then let's take a look and let's try to understand what exactly is happening here. So we have in this diagram, we have north and south. So we have the two permanent magnets on either side. And we have the flow, the magnetic field going mostly from north, as we can see, from north to south. So that is the magnetic field of the permanent magnet. Now, in the middle, what is showing there, that little yellow circle with a dot in the middle, that is the wire of the conductor. So we're seeing what is basically a cross section of the conductor. And as we can see, we have, following the right hand rule, the current is flowing towards us, which means the electric current is flowing, sorry, not the electric current. The magnetic field is going in a circular motion, anti-clockwise. So these are the two different magnetic fields, one in blue, one in green. Now, these two magnetic fields will interact with each other. You see, if you look carefully, the green magnetic field, some of the arrows are going in the same direction. Some of the green arrows, I should say, are going in the same direction as some of the blue arrows. However, in some parts, the green arrows are actually going against the blue arrows. So that's the very important thing, because when these two arrows or these two forces interact, what happens is it becomes something like this. Okay? So what actually happens here is, let me go back up here. When we have the arrows going in the same direction, meaning to say they're both going in the same directions, basically what that means is that when all the arrows are going in the same direction, when all the magnetic field lines are going in the same direction, it makes that part of the magnetic field stronger. That's what it means. Because they're both doing the same things. They basically combine to create a greater magnetic force. However, on the other side, when the two magnetic lines are going in the opposite directions, what it means is that it actually makes the magnetic field on this side weaker. So that's the concept here. On one side, we have a stronger side. On the other side, we have a weaker side. So what happens then? So what happens is that you have a sort of imbalance in power. What I mean by imbalance in power is that one side is you have a stronger magnetic field. And on the other side, you have a way weaker magnetic field. This difference, and it's this difference in the magnetic field that causes a force, right? When everything is the same, then nothing's going to change. But when there's an imbalance, one side is stronger than the other, it causes a force. It ends up pushing the conductor. And so now you're able to imagine now how that applies for things like electric motors, right? And maybe you'll also remember if you've ever tried to open one of those little electric motors in those little toy cars that we used to play as kids. Those little electric motors have magnets in them, if you remember. They have magnets in them, and they also have current-carrying conductors or wires inside them. And so they are basically using the same principle, where by having two magnetic fields that are interacting with each other, we can produce a force that causes motion. And so that is the basic principle of how every single type of electric motor works. Okay, wait, sorry. Yeah, so that is the basic principle of how all the electric motor works. Now, it does get a little bit more complicated when we start to take into account things like direct current, alternating current, the different shapes of the conductor. But this is the basic principle. So make sure you understand at least this basic principle before we go on. So Fleming's left-hand rule. So how do we determine the direction of the force? Excuse me. So the direction of the force on a current carrying conductor can be determined by using Fleming's left-hand rule, as shown is in figure 4.4. Again, that's in your textbook. The picture is a little bit small. Let me zoom it in. But basically, you use your left hand, not your right hand, okay? Your right hand is for one thing, is for you to determine the direction of the current and the direction of the magnetic field. Your left hand is when we're trying to figure out where is the direction of the force. So basically, if you take your left hand and you make this sort of shape, so your thumb pointing up, your index finger pointing forward, and your middle finger pointing towards the right. If the current is flowing through the middle finger, so you imagine that your middle finger is the wire, the magnetic field, the direction of the magnetic field would be your index finger, and the direction of the force would be your thumb. So we can use that to predict the direction of the force. Excuse me. So yeah, then so index finger shows the direction of the magnetic field, so north to south, right? Middle finger shows the direction of the electric current. The thumb will show the direction of the force acting on the conductor, meaning to say the direction of the motion of the conductor, meaning to say the wire. The wire, when it's pushed by the electromagnetic force or whatever, the wire will go in the direction of the thumb. So basically, if we have something that looks like this, so we have two magnets. So the magnetic field of the magnet is going from north to south. We have the current going in this way. The force, these two things together will cause this wire to move up. At least relative to this picture, will go in an upward motion. So basically just like your three left-hand fingers there. So we have the current, we have the force of the magnets, we have the magnetic field, and we have the force, which will be the direction of the movement of the conductor. So you obviously can begin to see that if we design it properly, what we can do is we have something that keeps on turning and keeps on turning and keeps on turning without ever stopping. Sorry. Okay. If you have any questions at any time, go ahead and type it, okay? Factors affecting the magnitude of the force on a current carrying conductor in a magnetic field. So we've discussed about how the force happens. You know, it happens through the interaction between the different magnetic fields and such. Now the question is, what are the factors affecting the magnitude? Can we increase the amount of force? Well, of course, since that's the topic, the answer is obviously yes. So the two factors affecting the magnitude of the force acting on a current carrying conductor is this. So the magnitude of the force acting on a current carrying conductor in a magnetic field increases when, number one, either the magnitude of the current increases. So basically more power. More power, more electric power means, you know, a higher amount of magnetic force. So if you wanted your electric motor to move faster, a simple way is to add more power. You can try this with those. If you have any of those electric motors at home, you can try. With one battery, it'll move slower than if you use two batteries. If you use two batteries, it'll move faster. If you use three batteries, even faster. If you use four batteries, it might explode. And if you're like me as a kid and you try to, okay, Henry said hook it up to a car battery. That's probably still safer than what I tried to do when I was a kid. Just a side story. So when I was a kid, I played with those electric motors, but I had the bright idea of trying to plug it in directly into the socket. I found an empty plug, so I put the wires in the plug and then I plugged it in the socket. Let's just say it wasn't a very pleasant experience. Do not, under any circumstances, do that at home. With a car battery, you might just end up breaking the small electric motor. I imagine the electric motor has a limit to how much, the small one anyway, has a limit to how much energy it can take. So yeah, that elaborate what happened. So when I plugged it in, so basically what happened was I found a socket that didn't have any wires in it. So me being the young kid I was about, how old was I? I was like 11 or 12, I think. So I decided, okay, well, here's the positive and the negative terminal. Let me just connect those two wires to my to the socket, and then let me plug it in. And then when it plugged it in, what I felt like, it felt like someone took a piece of wood and hit me on the back, because from the electric socket, I was basically kicked back across the room. Luckily, on the other side of the room was my bed. So basically, I got kicked from my plug. It basically knocked me back all the way back to my bed. It felt like someone hit me with a baseball bat. I literally thought someone hit me with a baseball bat. So yeah, don't try that at home. That hurts. Okay, I was actually very lucky that it actually kicked me back instead of, the other thing that might happen when electricity is if you get like electrocuted and you get stuck. That's the most dangerous thing. But fortunately for me, I was just kicked back. So don't try that at home. Anyway, back to where we were. So obviously, by increasing the power, electric power, you increase the amount of force that happens. Your engine will move faster and faster. The other thing is, of course, to use stronger magnets. So if you have a small engine, those small little toy cars, they use small magnets. And then a bigger engine might use a bigger magnet. Or not might, but it definitely will use a bigger magnet. And if you look at it, actually, both of these things are actually kind of related to each other anyway, because when you increase the current in the wire, you're basically increasing the strength of the electromagnet. But this one, so you're kind of doing the same thing. You're basically increasing the magnetic field. But of course, this one is specifically talking about the permanent magnet. When you increase the power or the size of the permanent magnet, then you increase the possible amount of force that you could produce from this electric motor. So the effect of the current and increase in strength of magnetic field on the force can be observed from the height of the swing of the copper frame as shown in figure 4.6. So 4.6 is, of course, in your textbook. So let me zoom this again. So basically, you have an electric current in this little wire here, and you have these two magnets. So you have current 1, so it will swing a certain amount. Now, when you apply a higher amount of current, then it will swing further away. Or another thing is, you increase the magnetic field. So what he did here is we put the two magnetic poles closer to each other to increase the magnetic field strength, and it swings out even further and further away. So basically those two things, more magnets, more electricity equals more power. Okay, let me zoom out again. All right, yeah. So more magnets, more electricity, more power, basically. Makes sense. It's electromagnetism. So another way we can study, for us to study the factors, or another type of experiment, is basically doing the same thing, except instead of using a swing sort of like this, we basically put a piece of wire and we see how far we see how far the force will push away the wire. So figure 4.7 shows another way to study the factors that affect the magnitude of the force acting on a current carrying conductor in a magnetic field. The distance traveled d by the conductor represents the magnetic force. So d, they purposely let this piece of wire sort of hang loose, right? Hang free, so that it will be pushed away when there is an electric current. So the bigger the electric current, the further away it will be pushed, or the stronger the magnetic field, the further away it will be pushed. So same idea, just a different way of doing the experiment. They are both doing basically the same thing. All right, here. So effects of a current carrying coil in a magnetic field. So now we have the idea of using a coil. So instead of using instead of using a sort of straight wire or straight cable, some genius came up with the idea, or decided to ask, what if we use a coil sort of shape like this? So in this picture, it's just a simple coil. Of course, if you've ever seen electric motors, there are actually more coils than this. But what happens when we use a coil instead of just one straight wire? So figure 4.8 shows a rectangular coil formed by a piece of copper wire. When the coil is connected to a power supply, the current can flow through the coil it can either go from A, B, C, D, or from D, C, B, D, depending on how you connect it to the electric motor or to the electricity. So what is the effect on a coil if the coil carries a current in a magnetic field? So the thing about a coil is we have the current going in one direction. So you have A, B, then it turns around, and then from C to D is going in the opposite direction. So essentially, when we put this in an electric field, we now have, well, I'll show you what happens first. We now have basically two magnetic fields to deal with, both going in different directions. Well, maybe you can imagine. I'll go back to the explanation later. But maybe you can imagine what happens. Okay, so spoilers. It does this, right? Because of the way that the direction works and because of the way that magnetic field works. So on the strong magnetic field area now will be different because it's a coil. And so now, maybe you can imagine now, if we go back to this coil, you can imagine what happens is, because on one side the force is going up and the other side the force is going down, then the coil will start to spin and turn around. So this is the concept, or basic concept, between all electric motors. We're using coils of conductors to make it spin. Alright, so let me go back to the explanation. So what is the explanation? So the current carrying coil in a magnetic field will rotate about the axis of rotation. Of course, you need to let it be free to rotate lah. If it's not free to rotate, then of course it's not going to if you put it on something that's fixed, then of course it will not be able to rotate. But if you put it on something that's free to rotate, then it will rotate. So this rotation is due to a pair of forces of equal magnitude but opposite directions, like what I just showed. So this pair of forces is again caused by the interaction between the current carrying foil and the magnetic field from the permanent magnet. Okay, so figure 4.10, the one I showed you just now, shows the pair of forces acting on sides AB and CD on a current carrying coil. The interaction between the magnetic field from the current carrying coil and the magnetic field from the permanent magnet produces a catapult field, as shown in 4.12. This is all in the textbook. You can double check again later. The catapult field exerts a force on sides AB and CD of the coil respectively. This pair of forces rotates the coil. This turning effect on a current carrying coil in a magnetic field is the working principle of the direct current motor. So direct current, we know that direct current is current that only flows in one direction, compared to alternating current. Alternating current, it flows in both directions, it changes. But the direct current, and most of the batteries that, so things like batteries, those car batteries, those are all examples of direct current electricity. And so this is what it looks like. So we have the current flowing in one direction, coming back and flowing in a different direction, which means the force will be also in different directions. Equal, because there's an equal amount of current on both sides, but different directions, one going up and one going down. So as long as this thing is allowed to rotate, it will rotate. And it will look like this. So when the magnetic fields combine and interact, so on the parts where the arrows are against each other, it becomes weaker. On the parts where the arrows are in the same direction, the field becomes stronger. And so you get a resultant magnetic field that causes it to rotate. By the way, I forgot to mention this earlier. These symbols, the yellow with a black dot and the yellow with an X, they both have different meanings. So let me double check. If you check on your textbook, I forgot to put this in the slide, but in page 138 in your textbook, it explains. So if it's a yellow dot, if it's a dot and a circle, it means that the direction of the current is towards you, right? So the dot means it's going towards you, while if it's an X, it's going away from you or inside the X. Basically, for the dot, it's coming out, and for the X, it's going in. So just so you know, when you're seeing pictures like this, you have to take note of whether it's a dot on X for you to figure out where exactly it's going to be. All right, let me go back. Okay, so direct current, that's a type of current motor. So small electrical appliances such as children's toys, portable drills, and the hard disk of a computer have a small direct current motor, okay? Larger direct current motors are found in machines such as electric vehicles. So, I remember Henry asked this, was it the last chapter? Are electric vehicles using the same concept? Yes, they are using the same concept. So, electric vehicles, lifts, and rollers in factories. So, the direct current motor changes electric energy to kinetic energy by using the turning effect of a current carrying coil in a magnetic field. So the concepts that we just saw, the ideas that we just saw, that is the basis of the electric motor. And any other type of electric motor, washing machines and what else can I think of? Fans are all using the same or using similar concepts. Alright, so figure 4.13 shows a direct current motor during the first half and the second half of its rotation. An important component is the commutator that rotates with the rectangular coil. The carbon brushes in contact with the commutator are in their fixed position. So let me just show you what's happening here. So what you see here is, this is the coil, and hopefully I can explain this properly. So you have the coil and the current is going A, B, C, D, right? So that's the direction of the, that is the direction of the electric current, which causes a rotation anti-clockwise, according to these magnets. Now you notice that, first of all, we have the commutator. So the commutator are these two things at the end of the coil, and each end of the coil has its own commutator, and there's actually a gap between these two commutators. And then we have these two carbon brushes that touches the commutator, which causes it to complete the circuit. Right? I'll read this later. But when it rotates, what it actually happens is there's a break between these two commutators, because after it rotates, what happens here is that now the electricity is flowing in the opposite direction of the coil. Instead of ABCD, is going from DCBD. And you need to be able to do that because we want it to continue turning in the same direction. So we do that so that the current can continue flowing in the same direction, not the same direction, but the rotation continues to happen in the same direction. Because if you think about it, if we just use a normal wire and we don't have this break between the two sides, what happens is when it turns, then the electric current now starts to flow in the opposite direction, right? If you just connect it like that. And so instead of turning round and round, it'll just go back and forth like this. So in order for it to continue turning in the same direction, this is what we do. We use this sort of concept so that it will keep on going on and on in the same direction. So let's read what it says here. So carbon brush X in contact with red half of the commutator and Y in contact with the blue half. All right. So direction of the current is ABCD. Okay. So AB of the coil acts downwards and side CD of the coil force acts upwards. So coil rotates in one direction. And when we go to the other side, it's the opposite. So now X is in contact with the blue half, Y is in contact with the red half, and the direction of the current is DCBD, is upside down. But that's okay because the coil is also upside down, which means, sorry, I made a mistake there. Which means ultimately that, even though the forces are acting on opposite sides, at the end of the day, the coil continues to rotate in the same direction as the first half of the rotation. So this design here, where we have a break between the two commutators and the coil turns around and round and round in one direction, this design is what we call a brushed motor. Because it's called a brushed motor because we have these carbon brushes. They brush against the commutator. And so the coil keeps on going round and round. So this is a very common design lah. It's a very common design for a lot of motors. However, there is one more type of design. Okay, before I go into the type of designs, factors affecting the speed of rotation of an electric motor. I think it's pretty obvious. So speed of rotation of an electric motor increases when, one, you increase more power. More power means more speed. Okay. Obviously, again, more strength. So the strength of magnetic field increases. Yeah, which is almost the same thing because increasing the current also increases magnetic field strength. But when I say strength of magnetic field, we're also talking about increasing using stronger permanent magnets, and coil with more turns, because the more turns they have, then it basically increases or decreases the total amount of force again. So these are all basically increasing the magnetic force. Now back to what I was talking about. There are basically two types of design. So this is a more common design where the coil is turning around and they use a brush and a commutator. A different type of design is what you have, what you call this. So if you ever, activity 4.7 is basically an activity where you look at different types of electric motors. So you might see that some electric motors do not use this. They do not use a commutator and do not use carbon brushes. So what it does instead, it looks something like this. And so if you look at it, the main difference is, you can see it on the brush motor, there's the commutator. And on the commutator, there are gaps. There are gaps between the commutators so that you can change the direction of the electric current. Now, in this brushless motor, there is no gap. Right? The coils are like this and there's a magnet outside. And you also notice that the magnet is basically just one round magnet. So what are the differences and what are the advantages? So these are basically all the differences. So the similarities, okay, both use magnet and a coil. So both are using the exact same concept. And both uses magnetic force to produce rotation. Now the differences are, and this is interesting. So for a brush motor, we saw that the magnet is stationary and the coil is rotating. However, it's the opposite for the brushless motor. The coil is stationary, it's the magnet that rotates. So because it's the magnet that rotates instead of the coil, there is no need for the brush. There is no need to keep on changing the direction of the circuit in the coil because the coil is not turning. It's the magnet that's turning. Another difference is that for an electric brush motor, there is some friction between the carbon brush and the commutator, which causes the carbon brush to wear out. So, every now and then you do need to replace the carbon brush. There is no carbon brushes, so no friction between the brushes and the commutator. That's for a brushless motor. The next is sparking at the commutator. Because you keep on connecting and reconnecting the electric circuit, it causes sparks. It might be small, but there is some sparks, which is technically it wastes electricity and produces heat. So it wastes a little bit of energy. No sparking at the commutator because the circuit never actually stops. And a brush motor has a louder operational noise, whereas a brushless motor has a softer operational sound. So brushless motors you would find when it's important for the motor to be not so loud. So for certain circumstances, so for things like maybe even things like air conditioning or anything, household appliances basically. Some of them, probably the more expensive ones that have a softer sound, would use a brushed motor. They also probably last a little bit longer because there's no friction. Yeah, and no sparking at the commutator. So those are the different. It's basically a different design of electric motor, but the principle remains the same, where it's using the interactions between the magnetic fields to cause a movement and cause a rotation and produce power and force and do all kinds of things. And that's basically everything for chapter 1. I mean, not chapter 1, sorry, for topic 1. So those are all the topics that we have here. We could go into topic 2, but there's a lot of concepts here, so I want you to be able to understand the concepts. And so I'm not going to go into topic 2. We'll go into that next week, which would be electromagnetic induction. So do you have any questions about magnetic fields or some of the practical applications? Or I'm not really an engineer, so I can't really talk too much about electric motor designs, but about the different principles that we have studied. Any questions? A toothbrush motor. So how does a toothbrush motor work? I've never, come to think of it, I've never actually used a toothbrush with a motor. I've always used the traditional type of motor. So I have some pictures here. Okay, I just clicked on Google to take a look at some pictures. Let me just show you a picture I found on Google. Wait, no, that's not the picture I wanted to show. So that's the picture. That's kind of what it looks like. This is an old design. So basically, this is one design. There are several designs of electric toothbrush. So this one This is the kind of electric toothbrush where the head is actually rotating. So basically it's using an electric motor, and then by using gears and different types of gears, it actually makes this head here rotate. So it's using the same principle. It's using the same principle. The other type of electric toothbrush, the one where it just goes from side to side, I imagine it uses a similar concept. The direction of the movement of remember the direction of the toothbrush is not only just based on the motor, but also based on the how you set up the gears and set up all the different components. Those are also things that what is this? Those are also things that we can do or use to change direction of the movement of the motors. So it's not necessarily just the motor that decides the final direction of the movement. Any other questions? How about the others? It's a very interesting. I mean, for me at least, it's a very interesting topic because it's interesting how they managed to take these forces. It's interesting how they managed to find these things out, and then use this concept as principles to basically make life easier. You know. Okay, so it seems like there are no other questions at the moment. So the lesson's a little bit shorter today. So a little bit easier for your brains this week compared to all the different things that we have. Okay, are the tracks in electric trains permanent magnets? Okay, that's a good question. Let me check Google. Electric train. How it works. That's a good question. How do electric trains work? Let me take a look at the picture and see if I can find one. Okay, wait. There are some pictures I see, but I want a simple explanation. Okay, here. This might be simple. Okay, are you talking about... Sorry, I forgot. No, okay, so... I forgot that there are two types of electric trains. So, a normal electric train does not actually... The tracks are not actually permanent magnets for a normal electric train. For your normal electric train, the electricity is just powering the engine normally. So, the magnets would be in the engine. So, basically, it's either... the electricity either comes from the track, or I think if you see some trains that connect to a cable overhead, there are some trains that look like that. That's actually connecting to an electric source. So that's for a normal electric train. Now the other type of train, however, what you're thinking about is maybe what we call a maglev train or a magnetic levitation train. Now those okay, so here's a picture of how a magnetic let me show you first this picture. This is what we call a maglev or magnetic levitation train. This is the basic principle, right? They are magnets. And they are on both the train and the on both the train and the both on the train and both on the tracks. So both are magnetic. However, let me just check. So the one on the train is definitely a... Okay, I let me be honest. I'm not really sure if it's a permanent magnet or a electromagnet. I assume it's probably an electromagnet, because uh, because of, you know, first of all, it's probably going to be pretty hard to get that many permanent magnets. The other thing is, if they are both electromagnets, it also means that it's easier for you to control, um, the speed of the train. It's possible that the train is the one that's using permanent magnets, and then it's the tracks that are using electromagnets. Let me check. Let me see if I can find a. Okay, so okay, so let me just share an article with you. There you go. You could read that. That's a good article. There's actually more to it. So I'll just read a few sentences from this article. Here's what it says. A maglev train car is just a box with magnets on the four corners. Okay? That's basically a simplification. Now, the magnets that they are using, this is interesting. The magnets that they're using are superconductors or superconducting, which means that when they are cooled to less than 450 degrees Fahrenheit below zero, they can generate magnetic fields up to 10 times stronger than ordinary electromagnets, enough to suspend and propel a train. So they're using electromagnets. That's what I thought, because when you're making a train, you want it to be something that you can control. You know, you definitely when it's a big object like a train, you definitely do not want something that you can't control. Let me read a few other things. So these magnetic fields interact with simple metallic loops set into the concrete walls of the maglev guideway, meaning to say the trails, the tracks. The loops are made out of conductive materials like aluminum, and when a magnetic field moves by, it creates an electric current that generates another magnetic field. So basically, it's all using electromagnetism. It's all using electromagnetism, which makes sense because you want to be able to control everything. Like you want to be able to really set, like, okay, let's put this much power so that we can use this much speed, and so on and so forth. Excuse me. Rideable railgun. Basically, yeah, a rideable railgun. Just as a reminder, so these magnetic trains, like which are, by the way, pretty fast and pretty quiet compared to a normal trains. They don't usually operate at full power. You know, when they try to break records, then yes, they will use. Sorry. When they're trying to break the record, then yes, they will use full power. But when they're just doing operation, they're not going to do full power because, they want to have a certain amount of safety. But yeah, basically a rideable railgun. Okay, what did Henry share? Okay, so that's basically a railgun. Military railgun. Yeah. So, of course, military. Actually, since you brought up the idea of a military, a lot of we're going off topic, but never mind. We have time. A lot of technology, including electromagnetism, a lot of it is originally developed because of things like military and army and wars and these kinds of stuff. For example, the internet, like what we're using. Originally, the idea of the internet was created as a sort of network for military communications. And then later on, they developed the technology and it becomes available to, the general public. And a lot of these things happen like this. technology that is first created for the military, and then as they continue to create it, it later becomes more accessible to the general public. So even though, war and things like that is obviously not a good thing, but at the same time, all the research that they put into war and into military does seem to serve as a motivation in trying to increase technology, which in turn does increase technology overall. A little bit of a side tangent there, but it's an interesting thing. Okay, so we've reached the end of our topic. So thank you everyone for listening. I will see you all. Basically, I will see you all next week, where we'll be talking about. We'll see how much we can finish. If we can finish the whole chapter next week, that will be great. So that we can go into chapter 5. But I have a feeling we might not be able to. We'll see. Okay, so thank you everyone. You may leave, and I will see you next week.